Hi, welcome to another session of Circuits and Networks. In today's transient class analysis, that is in class 8, we are going to see different numericals on the behavior of RL circuit and how to find out the transient current in particular RL circuits. So you can see in these two particular cases, these are two different problems where you can see the switching position is moved from A to B and we need to find out the transient current. Similarly, you have another circuit which is composing of three loops. Here we have two voltage sources in this problem one, whereas in this another problem we have only one current source. So how to deal these kind of problems in transient analysis and how to find out the transient current is our interest. So this we are treating as class 8. In our next class, you are going to see the same numericals. So with capacitor placed parallel to resistor or in series with resistor. And in fact, we are going to see different arrangements of passive elements either in series or in parallel or the combination of series in parallel and how to find out the transient current using differential approach. Okay, so let us begin with our basics, what we have learned in our previous classes. So what we have learned from our previous classes that the transient current of series RL circuit, for example, this is a series RL circuit where the circuit is closed. In this figure 1, when the circuit is closed, this is how the circuit looks like. And when the current starts flowing, we have derived that I of t is equal to whatever the input voltage is there and whatever the resistance is there, that is the amplitude value V in by R, open bracket 1 minus e to the power of minus R by LT. So R by L, it is known as the time constant, and we got the graph of transient current to be exponential rising. So this equation 1, when you are going to apply the different values of constant parameters, that is time constant parameters, where time constant tau is equal to R by L, you are going to get the exponential rising characteristics like this. So this is what we have learned from our class 7, and we have obtained the exponential rising curve for the equation 1 which is shown over here. So this is what we have learned from our last class. Now whatever we have learned from our last class, if at all we try to implement the same analysis in order to obtain the voltage developed across resistor or voltage developed across inductor when the transient current I of t is equal to V in by R 1 minus e to the power of minus R by LT. So this information, and with this information, if at all we want to obtain VR and VL. So can we do that or not? Yes, we can do that. Because from Ohm's law we know that VR of t is equal to R into I of t. So this is according to Ohm's law. Now I'm substituting the value of I of t, which is V in by R 1 minus e to the power of minus R by LT, and here you have R component and VR of t you have R into I of t component. So R and R, they both get cancelled and we are going to left over with VR of t. So this RL circuit which is equal to V in of 1 minus e to the power of minus R by LT. Let me remind you, R by L is known as time constant. So what we have come to the conclusion that the voltage developed across resistance will be equivalent to the rising characteristics of the circuit. So if that is true, this is how the circuit looks like. So the circuit is shown in figure 1e. In fact, this is a graph of VR of t when it is going to get applied across t. So this t is the ranging parameter. So R by L, whatever it is there, that is the time constant. Just time constant you have to replace with the varying values of t, and this is the graph which you are going to obtain for voltage developed across resistor when V in is applied and I of t is flowing in the circuit. If that is true, what would be the value of voltage across inductor? So we know that VL of t is equal to LdI by dt. This is from Faraday's law of electromagnetic induction. When you are going to apply I of t, which we have obtained in this equation, so d by dt of V in by R of 1 minus e to the power of minus R by LT. So just I have taken V in by R outside. I have L as it is, and I have applied d by dt to I of t, which is the main parameter, which is nothing but 1 minus e to the power of minus R by LT. So apply differentiation to these parameter. Differentiation of 1 is 0, and differentiation of minus e to the power of minus R by LT. So differentiation of e to the power of alpha t, or what we can say the value of constant, we are going to get the value as, you can see, L, it is as it is, V in by R, it is as it is, differentiation of 1 is 0, minus as it is. Now differentiation of e to the power of minus R by LT is nothing but e to the power of minus R by LT. But we have to take the differentiation of inner parameter of e to the power of minus alpha t. Alpha is R by L or tau, what you can call. So e to the power of minus R by LT differentiation will again lead to the constant parameter as minus R by L. Now with this R and this R will cancel out, L and L will cancel out, and hence we are going to remain with V in e to the power of minus R by LT. Here we have minus, here we have minus, so both will get cancelled. So that is how we got the value of VL of t is equal to V in times e to the power of minus R by LT. Now what kind of graph we are going to obtain with this equation 3? When you substitute the value of time constant tau is equal to R by L, when you substitute the values for different values of this t, we are going to get the graph in this fashion. So in fact, the inductor voltage is decaying, exponentially decaying. So this is the graph what we are going to get when you are going to employ VL of t for I of t, which is equivalent to this value. I hope you understood how we got the graph of VR and VL from equation 2 and equation 3. If at all you have any doubts in these graphs, please comment in the chat box whatever the doubts you have, and let me know wherever you find a difficulty to understand these two graphs according to the equation 2 and 3. So we'll switch on to the main concept. In figure 2 you can see we have a problem 1 where the switch is initially at position A. On the steady state having reached, the position of the switch is moved to B. Means what? Initially the switch position was at A and the steady state conditions have reached. इसका मतलब क्या है? We have the switching condition at A and 24 volts is connected to 4 ohms. So you can see that 24 is in series with 4. So both are in series, and the series combination is also in series with 8 millihenries, and the steady state conditions have reached. What do you mean by that? इसका मतलब क्या है? The inductor is connected to 24 volts where the switching position is at A. So sometimes I'm using Hindi because some of my users, they have commented in the chat box that please use Hindi language in order to understand this concept in a better way. Anyhow, it is, if it are providing any problem to you, please answer in the chat box, whatever. So just imagine the switching position as at A. Means what? The switch is at position A and the steady state conditions have reached. Okay. At that position, what is the current flowing in the circuit? Based on that, we have to derive the current I of t after the switching position is moved from A to B. So that is what it is given the problem. So the solution starts with the given condition, that is at t equal to 0 minus, means what? The switch was in position 1. When the switch was at position 1, the circuit will be shown in figure this 2a. So you can see this is the circuit. आप समझ सकते हैं कि ये सर्किट कैसा आया है. ये circuit which is shown in figure 2a, it is based on the standard switching conditions of inductor. So that condition we are treating as I of 0 minus. So 0 minus is the switching condition before it has reached to B. इसका मतलब क्या है? स्विच ए पे था और करंट वॉट एवर जो भी करंट था भी जो 8 मिली हेनरीज के अंदर फ्लो कर रहा था उसका वैल्यू क्या है, बिकॉज इंडक्टर है, दैट इज व्हाई दिस इज शॉर्ट सर्किट. Okay, this current can be easily obtained with the analysis of inductor as short circuit. इंडक्टर का जो बिहेवियर है अंडर स्टेडी स्टेट कंडीशंस, it will act as short circuit. So the value of current will be, according to Ohm's law, V equal to IR. So we have voltage as 24 and resistor as 4 ohms. So I of 0 minus will be equivalent to, because it's a closed circuit, you have resistor and voltage. So the value will be 24 by 4, which is equal to 6 amperes. Now this is the value of current, and what is the standard property of inductor? That the current in the inductor cannot change instantaneously. Means what? Immediately after switching also, तब का तब अगर पोजीशन A से पोजीशन B को अगर स्विच मूव करता है तो इंडक्टर के अंदर जो भी करंट है या जो भी कंडीशन ऑफ करंट ऑफ इंडक्टर है वो चेंज नहीं होगा. It means what? I of 0 plus will also remain as 6 amperes. So I of 0 plus also will be equal to 6 amperes. Now with these conditions, let us go with the actual circuit for t greater than 0. So the network changes to figure 2c. Now you see, we have 24 volts and the position of the switches change from A to B. So when the position of the switches change from A to B, inductor already got charged. It has some current. The value of current is 6 amperes. And the current which is 6 amperes, it is flowing in the inductor. And this we have to take in our mind. Means what? इंडक्टर के अंदर जो भी करंट फ्लो हो रहा है वो है 6 amperes. That is the condition when it is moved from A to B. Now at condition B, 12 volts is connected. So this is the circuit which will be sustained after t greater than 0. इसका मतलब है स्विच का पोजीशन A से B को आ चुका है. अब जो सर्क्यूट है ये सर्क्यूट है. This is the circuit which is remained. Now with this we need to calculate I of t. What is that I of t? That is a transient current. इसका मतलब क्या है? जो कुछ भी इंडक्टर का करंट 8 मिली हेनरीज में डेवलप हुआ है, ये हमारा इनिशियल कंडीशंस है पर इस फिगर का. So with this we need to calculate what is a transient current. So we are left over with this loop which is having 12 volts, 4 ohms, 8 millihenries. So what I'll do, I'll apply KVL to this loop. I'll apply KVL to this loop. So minus 12, that is a voltage source which is connected, plus 4 into I, that is a drop, plus L di by dt. L value is 8 millihenries, di by dt equal to 0. Is this clear? Right, this is the main equation which we need to concentrate. So I'm treating this equation as equation 2, and I'm going to make use of equation 2 like this. You can clearly see di by dt is remained as it is. 8 millihenries is getting divided by 12 as well as by 4i. So 4 divided by 8 millihenries times I, which is equal to 12, taken on the right hand side, becomes 12 by 8 millihenries. So this particular equation changes to di by dt plus 500i is equal to 1500. Now this is a mathematical equation which we are treating as equation 3. So what kind of mathematical equation? It's a non-homogeneous equation. Its general form is di by dt plus pi is equal to q, where p is equal to 500, q is equal to 1500. So what is the solution for this particular non-homogeneous equation? The solution for this particular non-homogeneous equation is given as I of t is equal to e to the power of minus pt integral q e to the power of p dt plus k e to the power of minus pt. So I'm going to replace the value of p, the value of q in equation 3. So this is how the equation is framed. कहने का मतलब ये है कि द ट्रांजिएंट करंट जो भी है वो इन मैथमेटिकल एनालिसिस पे डिपेंड करता है. इसका इंफॉर्मेशन आपको इंटरमीडिएट के टेक्स्ट बुक्स में मिल जाएगा कि हाउ टू फाइंड आउट द जनरल सॉल्यूशन फॉर नॉन होमोजेनियस इक्वेशन. So application of mathematics in electrical engineering. So this is one of the main important part. So e to the power of minus pt, p is minus 500 and integral q is 1500. Again you have e to the power of pt, so e to the power of 500t dt plus k e to the power of minus 500t. So this we are treating as equation 4. Now when I'm going to take the integration of 1500 e to the power of 500t dt, so 1500 I'm going to take it as a constant, ये बाहर आ जाएगा, it will come out like this. So integration will be applied to e to the power of 500t dt. So integration of e to the power of a t or alpha t is nothing but e to the power of a t times multiplied with the constant value. So with this I have q value which is 1500 e to the power of minus 500t, that is this value, e to the power of minus 500t, and integration of e to the power of 500t is the value of integration of e to the power of 500t is nothing but e to the power of 500t. So this e to the power of 500t is the resultant of integration, and e to the power of minus 500t is a value already present in the outside of the equation. So these two will get cancelled out. E to the power of 500t integration is nothing but e to the power of 500t divided by 500. So q divided by this value plus k e to the power of minus 500t. Now we need to know what is the value of k. So this equation changes to 3 plus k e to the power of minus 500t. So this k is a constant which can be derived from the initial condition. So let us frame I of t is equal to equation 5, and from the initial conditions, what is the initial conditions? What is the value of the current which is flowing in 8 millihenries, that is 6 amperes. So I of 0 plus when I'm going to apply, I got the value as 6 amperes. Now this I'm going to apply over equation 5. So 3 plus k e to the power of 0t. Hence 6 minus 3 will remain the value as 3. So the constant, it is derived from the initial conditions whose value is 3. Just substitute the value of k in equation 5. That is equation 6 in equation 5. I'm going to get the value of I of t is equal to 3 plus 3 times e to the power of minus 500t. In fact, this is the value of the current, that is the transient current flowing in this circuit. So you please repeat the equations what is framed from 4, 5 and 6. Cross check how we got the value of I of t. Repeat the video in repeated mode for equation 4, 5, 6 for easy understand. I hope you have understood how you have framed I of t. If at all you have any doubts, let us go with this problem. In figure 3, the network is shown. The steady state conditions is reached when the switch is closed. Means what? The switch was initially closed, and after t equal to 0, the switch is open. With this, we need to find out what is the current which is flowing in inductor as well as the voltage developed in the inductor. So how do we solve this problem? So go with the basics. What is the basic? We know that at t equal to 0 minus, the circuit, it can be changed to this, which is exactly like this. Since the inductor is there and the steady state conditions are reached, inductor behaves as short circuit. So when the inductor is short circuited, 45 ohms is being shorted by inductor. So in fact we have a closed circuit which is having 120 volts in series with 60 ohms, and that is a closed circuit. So with this I'll get the value of current, that is the current when the switch was closed, which is equivalent to 2 amperes. So this is the information what I have obtained across the inductor when it is shorted. So it will remain as it is. So I of 0 plus is also 2 amperes. So this is the step 1. Okay. Now when the current is not changed in the inductor, that is I of 0 minus and I of 0 plus, it is 2 amperes. And as soon as you are going to make use of the switch close conditions, switch open conditions, inductor is having the source current. So this is how the circuit will look like. So inductor is stored with 2 amperes and resistance 45 is connected to 0.15 henries. In fact, this circuit is changed to this circuit. Let me frame this equation as figure B. In fact, this is how the figure is framed 3B, where you have inductor charged with closed 45 ohms resistance. Okay, what we need to keep in our mind that inductor is stored with 2 amperes. Okay, so let us concentrate on this equation. Actually, we have only two parameters and we need to apply KVL to the circuit which is having 0.15 Henry, which is closed with 45 ohms. Okay, so current which is flowing I of t, that is what we need to determine. So I of t is the transient current. So applying KVL to this closed circuit, I have 45. So 45I plus 0.15 di by dt is equal to 0. Or you can start with 0.15 di by dt plus 45 is equal to 0. Now this we are treating as equation 2, and I am changing this equation by dividing 45I by 0.15, which will give you the value as di by dt plus 300I equal to 0. Now this equation is treated as 3. It resembles to a homogeneous equation. In general, homogeneous equation is given by di by dt plus pi is equal to 0. And the solution for this homogeneous equation is obtained as I of t is equal to k times e to the power of minus pt, where you can find out the value of k with the help of initial conditions. So as of now, I can obtain the value of I of t of equation 3, which is equal to k times e to the power of minus 300t, where the value of p is 300. Okay, as I told you, k can be determined from the initial conditions. So this equation 4 can be easily obtained with the help of equation 1. What is that equation 1? I of 0 plus is equal to 2 amperes. So applying 2 amperes is equal to k times e to the power of minus 300 times 0, which will give you the value of k, which is equal to 2. What is this 2? This is the value of current. So here there is a small mistake. So here it is not 3, it is 2. Okay, it's a small mistake over here. K should be equal to 2. So anyhow, I'm going to substitute the value of k, which is I of t is equal to 2 into e to the power of minus 300t. So that is the value of I of t. Now that is the first case what we require. What is another case? Another case we require VL of t. So VL of t is given by L di by dt. So L value is 0.15 d by dt times of 2 e to the power of minus 300t. So this is I of t what we got in equation 5. So just substitute the value of I of t. So 2 multiplied with 0.15 will give you the value as 0.3 e to the power of minus 300t. Differentiation of e to the power of minus alpha t, which is equal to e to the power of minus alpha t times minus alpha. So minus alpha is minus 300. So 300 multiplied to 0.3 will give you the value as minus 90 e to the power of minus 300 t volts. So this is how we solve the transient analysis problems, especially when we're dealing with inductors in series or parallel with resistors. Let us have a quick review of whatever analysis we have done in this figure 4. The switch Initially it was open, okay, and it is closed at t equal to 0. We need to find out IL of t, which is flowing through 2.4 henries. So according to our analysis, at t equal to 0 minus, the circuit is already shown, it is open circuit, so the current which is there, it is not going to flow to this particular parameters, it will flow only to 4 ohms. So in fact IL of t is 0. How it is 0? Because I of 0 minus is 0 amperes, and inductor doesn't allow sudden change in current, so I of 0 plus is also 0 amperes, and hence IL of 0 plus is also 0 amperes. For t greater than 0, when the switch is closed immediately, the circuit it will look like this. Okay, this is how the circuit look like. What we need to find out? We need to find out the current, which is IL of t flowing in 2.4 henries. So this current we need to know. What I have done, I have done a small operation over here when 4 and 2 are in parallel. So parallel of 4 and 2 we giving the value as 4 into 2 by 4 plus 2, which is 8 by 6, is equal to 1.33. So I've just replaced this parallel circuit with this circuit 1.33 ohms, and the rest of the circuit is as it is. Am I clear? I have just changed this circuit to this circuit because my intention is to find out the IL of t in 2.4 henries, and 6 amperes it is kept as it is. Only this parallel arrangement of 4 and 2 is changed to 1.33 ohms. I hope you understood this step. What I require IL of t. There is a tangent current. So I'll do that. And this is a small alteration is done. Okay? Right. So after doing this alteration, you can see 6 amperes parallel to 1.33 ohms. According to the source transformation, it can be changed to voltage in series with resistor 1.33, and I can connect this circuit with the help of voltage in series with 1.33. So I'm going to do that. I know that V equal to IR, and I value is 6, R value is 1.33. So it will change it to 7.98 volts. So V value can be equivalent to 7.98 volts, and that should be kept in series with resistor R. And this circuit you can see is changed to this circuit, where we are not changing 2.4 henries parameters, that is IL of t, in fact I of t. Only this circuit is changed to this circuit. Is this clear? Please comment in the chat box whether you have understood this step or not. It's a simple step. Whatever the requirement is there, the requirement is not changed. Only the other part of the circuit it is simplified. That is 6 amperes in parallel with 1.33. It changed to 7.98 in series with 1.33, and the rest of the circuit is connected as it is. That is 4 in series with 2.4 henries. It is kept as it is. Our intention is to find out I of t or IL of t, that is not changed. Now I'm going to apply KVL to this. So I have minus 7.98 volts plus 1.3 times I of t plus 4I plus 2.4 di by dt. So this can be simplified as 1.33 plus 4 will be 5.33I plus 2.4 di by dt, which is equal to 7.98. And in fact, this can be changed to a type of non-homogeneous equation, which is di by dt plus 2.2I, which is equal to 3.325. Now, this is in the form of di by dt plus pi, which is equal to q, where p is 2.22 and q is 3.325. So, what will be the general solution for this? The general solution is equal to I of t is equal to e to the power of minus pt. So, e to the power of minus 2.22 t integral q e to the power of pt dt. So, q value is 3.325 and p value is 2.22 t plus k e to the power of minus pt. So, p value is 2.22 t. So, this can be easily obtained as the integration of e to the power of 2.22 t is equal to e to the power of 2.22 divided by 2.22. So 3.325 divided by 2.25 will be 1.49 or approximately 1.5. This e to the power of minus 2.22t and e to the power of 2.22t will get cancelled, and we are left over with k multiplied with e to the power of minus 2.22t. So this is the general solution for this equation. We can easily obtain the value of k with the help of initial conditions. So initially the current was 0 amperes. So just substitute the value of 0 in I of t place. So 0 equal to 1.49 plus k times e to the power of minus 2.22 times 0. So hence the value of k will be minus 1.49, and just substitute the value of minus 1.49 in this equation to get the I of t, which is equal to 1.49 of 1 minus e to the power of minus 2.22t. So we can see we have employed each and every step by step in order to obtain the value of I of t, and this is how we solve the transient problems pertaining to RL circuit, whether they are arranged in series or in parallel. So this particular equation is the transient current equation for the circuit which is given in problem 3. So I hope you understood these two problems how we have solved. Okay. So please share among your friends and subscribe to my channel, and please press the bell icon for the future notification.